How goes it, everybody? We are starting in on chapter 17, which is all about nuclear chemistry in this video. Nuclear chemistry is actually one of my favorite topics to talk about in chemistry. It's partially because it's so different than everything else in chemistry. It's also very, very relevant to our lives, our modern day lives. And there's a lot of really cool topics in nuclear chemistry. So let's go ahead and jump into this here. When most people hear just the word nuclear, they don't really think science. What people think when they hear the word nuclear is death, destruction, radiation, cancer, the bomb. They think of all of the negative things that are attached to nuclear anything. All the bad stuff immediately comes to mind because that is what everybody talks about. Everybody talks about all the bad things that have happened, all the things that could go wrong, the potentially bad things. You'll hear about the Chernobyl, and you'll hear about Hiroshima and Nagasaki, and all these things. And what you won't hear about is all of the amazing things, all the very useful things that come out of nuclear chemistry. So, for example, the Voyager space probe that is now, I believe it's actually out beyond our solar system now, if I remember correctly. That actually is powered by a nuclear battery. If you think about the satellites that are above our planet right now, most of them are not run by nuclear batteries. Most of them have, well, I guess I shouldn't technically say that because I actually don't know that for sure, but a lot of them, at least, are not run by nuclear batteries. A lot of them use solar panels, like the International Space Station uses solar panels. It uses a lot of energy, and so it would take nuclear batteries. Just number one, are super expensive, but they probably wouldn't have enough to run the ISS. But Voyager, way out in the outer regions of the solar system, is not getting all that much sunlight out there. It's practically getting zero sunlight out there. It's very, very little sunlight. So solar panels would not work very well. So instead, they use nuclear batteries that work on the principle. There's a thing called, what's it called? It'll come to me later. But anyway, there's a very special kind of a joining of materials where you essentially have two different materials that are next to each other, and if there is and current will pass from one material into the other material if there's a circuit, obviously. Current will pass based on the temperature of the material. And so if you put something hot up against it, it will cause current to flow, but as it does that, whatever it is that's hot is going to naturally cool down, and so it doesn't happen infinitely. But nuclear material is hot for a really, really, really long time, just naturally. Nuclear material is very, very hot. If you have enough of it anyway, you can get it very, very hot. And so you can have this nuclear material that is hot just all of its own accord. You don't have to do anything to it. It is just naturally hot, and it can power that battery for as long as the material stays hot, which is a very, very long time. This is also why pacemakers, things that you put into people's chests, those also use nuclear batteries. They do not use lithium-ion batteries. There's not a recharging port or anything like that. They have nuclear batteries, so if you know someone with a pacemaker, most likely they have a little bit of radioactive material in their chest. Now, it's very well shielded, so it's not going to cause them very much harm anyway. It's having that in your chest, running your heart, is going to keep you alive a lot longer than the very minimal amount of damage that a little bit of radiation will do. And believe it or not, there's actually some good research that shows that a little bit of radiation is actually good for you, believe it or not. But pacemakers and satellites that go out into space, These things are run on nuclear batteries. There's also quite a bit of nuclear chemistry and nuclear physics in medical settings. A lot of the imaging methods that we use nuclear processes to make the image, like PET scans, for example, which I think we'll talk about just a little bit later, and the sun, which is the source of all life on the Earth. Like everything that has energy, really, goes back to the sun. Is where we get that energy from. Because if you think about the food chain, everything that's alive eats something else. Sometimes literally, sometimes more figuratively, but down at the bottom of the food chain is plant life. And where does plant life get its food from? Well, sunlight, among other things as well, but it would not be able to exist without sunlight. So the sun is very, very important, not just for keeping us warm, but for keeping us fed. So there's a whole lot of really amazing stuff that is attached to nuclear chemistry. It is not all death and destruction. So let's talk a little bit more about what's happening with nuclear chemistry. When we're talking about nuclear chemistry, we're really concerned with things that are radioactive. Because if something's not radioactive, then there's not really any point in talking about its nucleus. Its nucleus is very stable. It's not changing. But when it comes to nuclear chemistry, we're focused on things that are changing, where we actually have chemistry occurring in the nucleus. And this happens with radioactive isotopes of materials. So radioactivity is the release of tiny energetic particles by the nuclei of certain atoms. Up to this point, we've just been dealing with chemistry involving electrons, but now we're going to talk about chemistry happening down here in the nucleus. This is relatively rare, thank goodness. Radioactivity is relatively rare. But even that being said, there is actually radioactivity all around us. If you go out in your backyard, there is a small amount of thorium and uranium in the dirt and in the rocks in the dirt, which is always there no matter where you go on the Earth. If you have a granite tabletop in your house, your kitchen is more radioactive than the average kitchen because there is a, by no means dangerous, but more than average amount of uranium in granite than there is in average rocks. So it's all around us, but it is thankfully, the most elements and isotopes of elements are not radioactive. It is a select few, but there's quite a bit of those around, just not in large concentrations, thank goodness. So Marie Curie was actually one of the very first people to investigate radioactivity, and in fact she was the very first one to investigate it thoroughly. It was discovered by someone else, but the person that discovered it, whose name I cannot remember off the top of my head, that person discovered radioactivity and essentially just kind of thought, oh, that's interesting. Oh well, moving on. And they never really did anything with it. It was Marie Curie that really realized the importance of radioactivity and what that could mean for the world, really, for science in general. And so she and her husband as well did a lot of research on radioactivity. Unfortunately, it killed her, that research, because when they were first researching this, they had no idea that it was dangerous. Maybe they had an inkling and they just they didn't want to change their research habits, but they would have chunks of uranium just sitting out on countertops. Her husband licked a chunk of uranium. This was apparently a common thing to do back in the day. If you had an unknown material, you would lick it. Never, ever lick an unknown material. Most things, I would say, never ever lick. There's very few things in life that I would say, yes, lick that thing. But apparently this is something that they did back in the day. They would lick stuff and get some information from that. I actually went to a museum that housed some of her materials, like her notebooks and things like that, from when she was working on this stuff. I went on a trip to Poland for a conference once, and because that's where she was from. She was from Poland. She did most of her work in Paris, but she was born and raised in Poland, in Warsaw. believe. And the notebooks that they had of hers, they actually had to keep under lead-lined glass because they were still considered to be not like kill you immediately or anything like that, but had a high enough radioactivity that they needed to not be, the people that worked there shouldn't be exposed to them all the time. So it was pretty crazy, the experimental methods they used back in the day. But she did a lot of very important work. She discovered two new elements added to the periodic table. One of them was polonium, which she named after Poland, which again was her home country. And then she also discovered, I believe, radium. She discovered, which she named after the fact that she was investigating radiation. So radium, radiation. I'm pretty sure it's radium. You can double check me on that. It's either radium or radon, but I think it was radium. I get the two mixed up because not only are their names similar, they're like right next to each other in terms of their atomic number. But anyway, really amazing woman. And if you're interested in these types of things, if you're interested in doing some research on a woman that had a huge effect on the scientific community, I would highly encourage you to do some research on Marie Curie. All right, in the next video, we are going to pick up talking about the 4 different types of radioactivity and what happens in each of these different types of radioactive decay. So I will see you in the next video.